Hello, 171 class. This is your notes for section 3.5, Exponential Growth and Decay. So we're modeling data here, and this is, again, what one of the things that you're having to do on your functions project is model data. And we'll get into a little bit more detail how to do that in another video. But an exponential growth or decay model has this look to it where we have A naught, which just means some initial value. We start off with A naught, and we either grow or shrink depending on this value K that's up here in the exponent. So if K is positive, we have an increasing function because E is being raised to a positive number, and then if K is negative, we have a decreasing function. Okay, now these things, notice this looks like quadrant 1. Typically this is always quadrant 1. T is time passing, so it's moving to the right. Time's moving forward, and something's either growing or it's shrinking. If it's growing, we call it an exponential growth model. If it's decreasing, we call it an exponential decay model. And here is an example. This figure shows the U.S. population in millions for 5 years from 70 up to 2010. Okay, in 1970, the population was 203.3 million, and by 2010 it had grown to 308.7 million. So we want to find an exponential growth function that models this. And that may seem difficult. It may seem like it's something that you've never done before, but what we're being asked to do here is figure out A naught, what A naught is, and we're being asked to figure out what K is. Right. A and T are our actual variables here. It's like y and x, and like y equals mx plus b. If you think about y equals mx plus b, a line, y and x are the variables, and your goal is to find out what m and b are if you're given some data, some points, that is. Well, that's the same thing here. There's two variables, a and t, and then there's two what we call parameters, just like m and b in a line are parameters. A naught and k are the parameters here. So it's similar to finding the equation of a line, but it's also similar to what we did at the end of chapter 2 when we did variation and solving for k, same exact variable that we used in variation equations. So very similar concept. So what we're going to do here, it says find an exponential growth model that models data for 1970 through 2010. So 1970 is what we're starting from. That's the initial value, so that's A naught. So this 203.3 is going to be our A naught. So it's going to look like A equals 203.3 times e to the kt. Now our job is to find k. Well, that's where this other piece of information comes in. 2010, how much farther is that after 1970? That's 40 years later. So when t is 40, a is equal to 308.7. Alright, and once we set up that equation, 308.7 equals 203.3 e to the k times 40, got k times t. I'm going to rewrite that as 40k, just because that's the more standard way to write a number times a variable. But now we have an exponential equation to solve to figure out what k is. So it's very similar to those variation problems where we plug in the information we're given and use it to find k. It's just how we go about doing that's a little different because we have the need to bring logs into the equation. Alright, but I still, if I got an exponential equation, I want to isolate the exponential part. I'm going to leave this, even though it's an ugly fraction, I'm going to leave this in fractional form for now because I don't want to round this and then round again at the end. Alright, we want to round as few times as possible. Alright, I've got e to a power with the variable, so to get that variable isolated, to get it out of the power, I'm going to bring in natural logs. Alright, and now remember what happens when natural log and e get together. They wipe each other out, and you're left with just the exponent. Alright, and then if you look here, the last thing we're going to do is divide by 40. Okay, this is very similar to the work that you've done before when you're solving for an exponent. Alright, and if you look what we have here, we got an exact answer. Again, it's an ugly answer, but it's an exact answer. Natural log of this number divided by this number, all that divided by 40. So when I put that into my calculator, alright, just got to be careful with your parentheses. The natural log of all of this fraction in the parentheses, then divided by the 40. There's my value for k. So 0.0104 roughly. So now we've got a value for k. Okay, there's k in the original model. So we're going to go back and plug in that value for k right there, along with what we said a naught was, which was 203.3. Alright, and we end up with the model. A equals a naught is 203.3, e to the k is 0.0104, which we just got down here, times t. Alright, so there's our actual model. So we use the information given, we plug in, and we end up going through here and solving for the value for k, and then once we get k, we have our model, and we're ready to use it to do part B. Okay. Now let me show you this. All right. Your work when you solve for k in one of these, you plug in, you give some information. Your work is always going to be the same. You're always going to divide by this number that's in front of e. All right. Then you're going to take in the natural logs, and then you're going to end up dividing by the number in front of k. Every single time you ever solve for k, you'll do this. But look at what the numbers are in this expression that we plugged into our calculator. The natural log of 308.7 was the later time, the value at a later time. The 203.3 was the initial time. And then the 40 is how long it took to grow from this to this. Okay, so what is the little shortcut formula going on here? K is always going to be equal to the natural log of the fraction where the numerator is the later value, all right, the value that took place later in time, divided by the original value, and then you close that natural log off, and then you divide by the time it took to grow from the original value to the later value. All right. Now k, this is what k is. Remember, if k is a positive number, this is growing. If k is a negative number, then this thing is shrinking. Well, if the later value is bigger than the original value, then this is going to be a improper fraction. And anytime you take a log, natural log or otherwise, of an improper fraction, like for instance 5/3, you get a positive number. But if the later value was smaller than the original value, meaning that it decreased, it shrunk, you end up with a proper fraction. And if you take the natural log of a proper fraction, like 1/8 for instance, you get a negative number. The time it takes to go from the original value to the smaller value or bigger value is always positive. So you're either going to have the top situation, improper fraction, where you have a positive divided by positive, which means k is positive and you're growing, or if the later value is smaller and it decreased, you end up with a negative number divided by a positive, which would make k negative, which means it's shrinking. So it all works out every time if you just use this formula. K equals the natural log of the later value divided by the original value, all divided by the time it took to change from one to the other. All right, then part B says, by which year will the population reach 335 million? So we're going to use the model that we came up with in part A, and then 335 million is the population amount, so that's 335. Remember, again, in the model, you've got one variable and a second variable here. This is measured in time units. This is measured in other units. So this is not time. So that means that the 335 is this value. Okay, 203.3 e to the 0.0104 t. All right, and we're going to do the exact same work that we did in the last problem, meaning we're going to divide away this number. We're going to leave this as a fraction because we don't want to round. we're going to bring in natural logs to get rid of the e. Alright, that's going to come down, and then we're going to end up just dividing by that number. Alright, divide by 0.0104, I get t equals exactly natural log of 335 over 203.3. Then that's all divided by 0.0104. That's the exact answer. Again, you're going to be asked to approximate this. Alright, so I plug that into my calculator, hit enter. It gives me 48.0203. I add that to the original fact that this is from 1970, so I add that to 1970, and I get 2018 and some change. Okay, so this is actually 2018 has passed, and we're a little bit beyond that. So technically, we're sometimes in 2019, but if you just rounded that and put 2018, you would get credit for it. But technically, this would actually be 2019, since the decimal is beyond the 2018. But it's, if you wrote 2018 there as well, you'd get credit for it. It'd be fine. All right, but that's how you have to answer these questions. By which year? You got to understand that. Obviously, that's not going to be the year, but you need to hold on to that as long as you can to get the most, the best approximation you can get here at the end. Now, look at the work we did in the last one. We ended up, again, I said we had the same work. We got down to here, and this was the later value divided by the original value inside the log divided by the time it took. Well, if you look at the question that we have now, 335, that's the later value, that's the original value. But now this isn't the time it takes. That's what we're solving for. Now this is what? This is k. So what we end up with is little shortcuts. If you're solving for k, you can always do the natural log of your later value divided by your original value. Then divide all that by the time it took to grow or shrink from the original value to that later value. But if you're solving for t, you take your later value divided by your original value inside the log just like before. But this time you divide by whatever k is, the growth or decay rate. Make sure k has got the right sign, positive or negative, depending on what it had in the original model. But that's an easy way to solve for t, because it's always going to be that exact same work, the process to get it, so you'll always end up with something that looks like this.